Welcome to the deep dive. Today, we are taking you behind the curtain of, well, probably the most ambitious piece of distributed software ever engineered.
It's quite something.
We're not talking about a simple app or, a new programming language. We are diving deep into the plumbing of the entire internet.
We really are. We're dissecting the architecture of the robot, or spider, the system we call the web crawler. This is the unseen foundation.
Right.
If you've ever found an answer online, bought something, or just navigated the web using a search engine, well, this system is what made that interaction even possible.
And that's our mission today, pure system design. The core idea seems, deceptively simple. Start with the URL, follow the links you find, repeat.
Sounds easy enough.
But our task is to take that simple loop and scale it. Scale it to planetary proportions, handling all the chaos, the sheer volume, and sometimes the hostility of the public web. We want to understand the huge engineering decisions needed to pull that off.
And the scale is really where that simplicity just vanishes. To set the stage, if we're designing a modern search engine indexer, which is kind of the gold standard for crawler complexity.
Right, the big one.
We are talking about needing to download, bare minimum, 1 billion web pages every single month.
A billion, monthly.
Monthly. And that's not even a peak load number. That's the continuous baseline requirement just to keep a search index reasonably fresh. That figure right there is the hurdle. It separates simple scripts from massive distributed systems engineering.
Okay, a billion pages a month. That number alone basically guarantees complexity. We know the main driver is search engine indexing, collecting and updating pages so we can search them quickly.
Peoplebot, basically.
But what other sort of high-value roles do these massive crawlers fill? It can't just be about Google and search, right?
Oh, far from it. While search indexing is definitely the dominant use case, you've got at least 3 other really crucial applications that need similar systems. The second big one is web archiving.
Web archiving. So preserving data for history.
Precisely. It's about historical necessity, really. Websites die, domains lapse, data just vanishes every day. So you have institutions like the U.S. Library of Congress or the EU Web Archive. They operate enormous crawling systems, specifically to capture and preserve this digital history.
So future generations can see what the web looked like.
Exactly. Ensuring future historians, researchers, citizens, whoever, have access to what the web looked like years, even decades ago.
Yeah.
It's digital preservation, but, on a continental scale.
That makes total sense, preservation.
Yeah.
Okay, what about when the goal isn't looking back at history, but trying to find insights for, right now, for the future?
Right. That moves us into the realm of web mining. The web is just this colossal repository of human and corporate knowledge. It's the biggest ever assembled.
True.
So organizations use crawlers to discover useful, actionable intelligence from it. A prime example, high-level financial firms.
Okay, how so?
They program these really customized crawlers. They're designed to specifically hunt for and download certain documents. Think annual reports, shareholder meeting transcripts, press releases from thousands of global companies.
Yeah.
They're gathering raw intelligence at scale to inform, potentially billions of dollars in investment decisions. And they get it long before human analysts could possibly sift through all that material manually.
So the crawler becomes this specialized information weapon. It's focused only on specific target data, not trying to boil the whole ocean.
Exactly right. And the final key application area is web monitoring. Think about protecting intellectual property.
Like copyrights and trademarks.
Yeah. Companies like Digimarc, for example, use these spiders as global watchdogs. They crawl the web constantly looking for specific images or text patterns or even code snippets to track copyright and trademark infringements.
So they're finding pirated stuff.
Finding pirated content, unauthorized use, and reporting it. Their job is basically brand protection and legal compliance, but operating across the entire globe.
Okay, so indexing, archiving, mining, monitoring. That's a pretty wide range. Now let's zero back in on our main target, the search indexer. You gave us those simple steps: download, extract, repeat. But what are the hard numbers for our mission? What are the specific requirements that really define the complexity we're facing here?
Right. So for our high-performance, durable search indexer, the required parameters really dictate the design.
Okay.
First, main purpose, search engine indexing. That's clear.
Got it.
Second, volume. That number we mentioned, 1 billion pages per month, minimum.
1 billion, okay.
Third, content type. Initially, we'll focus on just HTML, but crucially, the design must be extensible later.
Right, so we can add images or PDFs down the line.
Exactly. Fourth, freshness. This is mandatory. The web changes constantly. We absolutely have to handle updates, deletions, new pages appearing all the time.
Can't have a stale index.
Nope. And fifth, storage. This one's big. We have to maintain 5 years of raw, archived content.
5 years of raw data. Okay, let's try to make that abstract volume a bit more tangible. Some back-of-the-envelope math usually helps crystallize the challenge.
Let's do it. Let's break down the implications of 1 billion pages monthly. So to hit that target consistently, we need to sustain a really high query rate.
QPS, right. Queries per second.
Right. Divide that billion pages over a 30-day month. You get roughly 400 pages per second, QPS, on average.
400 every second.
Every second. And given, the natural peaks and valleys of internet traffic, the system has to handle bursts. So our peak QPS capability probably needs to be closer to double that, maybe around 800 QPS.
Okay, 400 sustained, peak at 800. That's
Yes.
relentless, just constant fetching. What about the storage? That 5-year commitment sounds daunting.
The storage commitment is truly staggering. Let's be conservative. Assume the average raw HTML page size is maybe 500 kilobytes. Some are bigger, some smaller, but let's use that.
Okay, 500K per page.
1 billion pages at 500K each. That consumes 500 terabytes TB of storage.
Per month? 500 TB a month. Wow.
Now multiply that by 12 months in a year, and then by the 5 years of required archival storage.
500 times 12 is 6,000 TB, which is 6 petabytes, times 5 years. That brings us to 30 petabytes.
30 petabytes,
Uh-huh.
PB. That's the storage requirement just for the raw HTML.
30 petabytes. How much is that really?
Well, to put 30 PB into perspective, think about the U.S. Library of Congress's entire digital collection. Scans of historical documents, recordings, manuscripts, everything. That's probably well below 15 PB total.
So we need to store roughly double the entire Library of Congress digital archive.
Roughly double, yeah. And unlike an archive, our data needs to be constantly updated and ideally searchable. That sheer volume is why the design has to be laser-focused on distributed systems and really smart storage optimization from day one.
30 petabytes and 400 QPS baseline. Yeah, it's crystal clear we're talking serious engineering innovation here, not just, writing some code. Before we map out the specific components, let's nail down the 4 essential characteristics. What defines a good, successful, large-scale web crawler?
Okay, 4 key things. The first one is just unavoidable. Scalability.
Makes sense.
Given the volume, the speed,
Mm-hmm.
the system has to be incredibly efficient. It has to use massive parallelization. We absolutely must distribute the work across potentially thousands of machines. No single machine or even a small cluster could possibly handle this workload.
Okay, scalability. Then there's the fact that the web can be, messy, which means we need robustness.
Indeed. The web is messy. You hit malformed HTML, non-standard protocols, servers that just don't respond, sites actively trying to trick your bot.
Spider traps.
Spider traps, yeah. We'll get to those. The system needs industrial strength exception handling. It has to handle the inevitable crashes, loops, bad data gracefully without the whole thing just collapsing in a heap.
Okay, the third characteristic. This feels like maybe the most critical social contract in the whole operation. Politeness.
Well, politeness is absolutely everything. We are fundamentally guests on other people's servers. We cannot overwhelm a single website by blasting it with simultaneous requests.
Because that's basically a denial of service attack.
Exactly. If the system isn't meticulously designed to enforce strict rate limiting and specific delays between requests hitting the same host, it immediately becomes an unintentional, massive denial of service attack. And what happens then?
Yeah.
Our bot gets blocked permanently
Yeah.
by major hosts. Game over.
Right, you get blacklisted everywhere.
Yeah.
And finally, number 4 is extensibility. This is about future-proofing, right?
Totally. Extensibility means the architecture has to be modular. Let's say we launch focused only on static HTML. But next year, the business wants to add support for downloading images or PDFs, or maybe even some new content type like 3D models.
Which will happen.
It always happens. We need to be able to plug in a new PDF parser module, for instance, without having to rip apart and redesign the fundamental flow of the entire system. It protects the initial investment.
Okay, scalability, robustness, politeness, extensibility. Those 4 principles really anchor the design decisions. So with those in mind, let's dive into the high-level architecture. You mentioned an 11-component workflow. Where does the fuel for this massive machine actually come from? Where does it start?
It all starts with the seed URLs. For a system this big, picking your starting points isn't random, it's strategic.
How do you choose?
You often begin with known, high-quality directories or sites. Then you strategically partition the URL space, Maybe you divide the internet by geography, start with the most popular sites in different countries, or maybe divide by topic, focus initial seeds on major news outlets, big e-commerce sites, financial institutions, health organizations, things like that.
Got it. So once we have those initial seeds, they feed into what you call the most critical piece, the URL frontier.
The frontier really is the brain of the whole operation. It's the component that stores all the URLs that are waiting to be downloaded. Now, you could call it a queue, and fundamentally it is, but just calling it a FIFO queue is a massive understatement. We're going to dedicate a whole section to it later, but for now, just know it's highly intelligent. It's actively managing both the priority of URLs and that crucial politeness factor before it ever hands out the next URL to be fetched.
Okay, intriguing. So a URL leaves the smart frontier, and it immediately triggers the two components that do the actual fetching.
That's right. That would be the HTML downloader and the DNS resolver. The downloader is what makes the HTTP request, but before it can do that,
It needs the IP address.
exactly. It needs the IP address for the domain name. That's the job of the DNS resolver. It handles that translation, turns www.example.com into the numerical IP address the network needs. Once it has that, the downloader executes the fetch, pulls down the content, hopefully within our strict time limits.
Okay, now we have the raw content, but you said we need to validate this before we commit it to that precious 30 PB of storage.
Absolutely critical. The next step is the content parser. This component takes the raw HTML we just downloaded and does two key things. First, it checks for really malformed syntax, making sure the page isn't completely corrupted or broken. Second, it might normalize the content a bit for later processing.
And you mentioned it's crucial that this parser runs separately, asynchronously.
Yes, absolutely crucial separation.
Why not just parse it right there in the downloader thread immediately after fetching? Seems simpler.
It seems simpler, but it's a performance killer. Parsing and validation, especially on complex or, frankly, enormous web pages, can be computationally expensive. It can take time.
Okay.
We need those downloaders running at absolute peak speed, that 400 QPS target, to meet our volume goals. If we stick slow, complex validation logic directly into that high-speed downloader pipeline, we create a bottleneck. The whole system throttles down.
So one bad page could slow everything down.
Precisely. Keeping the parsers separate prevents a single badly formed page from crashing, or, more likely, just excessively slowing down that primary high-speed download process. It protects the throughput.
Makes sense. Okay, content is parsed. Now we need to filter out the waste. The content sane. Check. You mentioned a surprisingly large chunk of the web is redundant.
It's actually shocking when you see the numbers.
Yeah.
Our sources suggest that close to 29%, almost a third of public web pages, are effectively duplicate content.
Wow, 29%.
Yeah. Mirror sites, temporary redirects that didn't get cleaned up, simple boilerplate pages. To maintain efficiency, and maybe more importantly, to conserve our expensive 30 PB of storage, we must detect and just discard this redundancy. We simply cannot afford to compare 500 KB files, character by character, 400 times every second. It's impossible.
So how does the system do that check almost instantly?
We use cryptographic hashing or checksums.
Yeah.
When the content is parsed, the system calculates a unique, short, fixed-length fingerprint, the hash value of that page's content.
Like an MD5 or SHA hash?
Exactly, something like that. The content scene module then just compares this tiny hash value against its database of all previously seen hashes. If the hash matches one already in the database, boom, discard the page, it's a duplicate. If the hash is new, we treat the content as unique. This massive reduction in the size of the comparison from 500K down to maybe 32 or 64 bytes is the only way this check stays feasible at this scale.
Clever. Okay, so if the content passes the duplicate check, it's finally safe to store in the content storage. We know this needs to handle 30 PB. What's the typical storage strategy for something that massive?
It pretty much has to be a hybrid approach. Given the scale, the vast majority of that 30 PB has to reside on disk, likely highly distributed, sharded disk arrays for cost-effectiveness and parallelism.
But disk is slow for searching.
Right. So to maintain quick access for the search indexing side, the system usually identifies the most frequently accessed or maybe the highest priority pages and caches them in a massive distributed in-memory layer. This drastically reduces latency for common queries or updates. Most data on disk, hot data in memory.
Okay, makes sense. Hybrid storage. All right, we've successfully downloaded, validated, checked for duplicates, and stored the page. Now the system needs to close the loop, right? Extract new fuel for the fire.
That's the job of the URL extractor. It scans the HTML content we just stored, identifies all the anchor tags, and pulls out all the hyperlinks embedded within them.
And handles different kinds of links.
Yes, This component also has to handle necessary transformations, like converting any relative paths, a link like about.s.html into the fully qualified absolute URL, http://www.example.com@gs.html, by prepending the domain name it came from.
Got it. These newly extracted URLs then run through another filter, the URL filter.
Yep, this filter acts as the first line of defense against wasting resources on URLs we don't want or can't use. It's like a sophisticated sieve.
What does it filter out?
It uses predefined rules to exclude unwanted stuff. This could be filtering specific file extensions we aren't currently trying to crawl, like maybe .exe files or certain video formats. It also filters out links that have consistently returned errors in the past, or links pointing to specific sites that have been manually blacklisted, perhaps because they host spam or malware.
Okay, clean up the list. The filtered links then face their own duplication check, the URL scene.component. This is different from the content check, right? This is about preventing endless loops and not doing the same work over and over.
Absolutely vital. This component checks one simple thing. Has this specific URL ever been visited before? Or, just as importantly, is it already sitting in the URL frontier waiting to be processed?
Because if you re-add the same URL hundreds of times,
You just flood the queues and potentially get stuck in infinite recursion, crawling the same small set of pages forever. It wastes resources and prevents discovering new parts of the web. Now, for systems at this scale, the implementation of URL scene often uses the specialized data structure you might have heard of, a Bloom filter.
a Bloom filter. That sounds technical. Why use that instead of just, say, a standard hash table or a set? Seems easier.
A standard hash table gives you 100% accuracy. It tells you definitively yes or no if you've seen the URL.
Okay.
But it consumes a huge amount of memory when you're talking about potentially trillions of unique URLs seen over time.
Okay.
A Bloom filter is different. It's an extremely memory-efficient, probabilistic data structure. It can quickly tell you one of two things. Either this URL is definitely new, or this URL might have been seen before.
Might have been, so it's not certain.
Exactly. There's a small, tunable chance of a false positive, meaning the filter says, yeah, I've seen this URL, when actually you haven't. But at the scale of billions or trillions of URLs, the enormous memory savings and the incredible speed of checking usually outweigh that tiny risk of accidentally skipping one or two unique pages. It's an optimization born purely out of the extreme scale we're operating at.
Fascinating trade-off. Okay, so if the Bloom filter says the URL is definitely new, or maybe new, and we check a secondary source if needed, it goes back to the starting point, the URL frontier.
Back into the brain?
And it's also recorded somewhere, maybe in a simpler list or database we call URL storage, just confirming, yes, we have now visited or queued this URL.
Correct. That completes the loop.
Wow. Okay, that is a breathtakingly detailed workflow, from seed to storage and back again. That detailed workflow really helps understand all the moving parts. Now let's tackle what feels like the central intellectual challenge here, the traversal strategy itself. Conceptually, the web is like a giant directed graph, right? Pages are nodes, links are edges.
That's the standard model, yes.
So we have our classic graph traversal algorithms from computer science, DFS, depth-first search, and BFS, breadth-first search. Why not just use one of those?
Well, for almost any large-scale web crawler, DFS is pretty much rejected right out of the gate.
Why?
Because web paths can be arbitrarily and sometimes profoundly deep. Imagine your crawler starts on a domain that has, say, a dynamically generated, never-ending calendar structure where every day links to the next forever, or just a poorly maintained site with endless directory recursion, like foobar.
Right, it could go down a rabbit hole.
Exactly. DFS would dive deep into that single, narrow, potentially very low-value path. It could spend hours, maybe days, just generating useless URLs within that one broken site while completely ignoring the vast majority of the high-value web it hasn't even touched yet. It's just too risky.
Okay, so DFS is out. That leaves BFS, breadth-first search, as the accepted standard. Treat the web like levels, explore level by level using a queue. Ensures you cover ground more broadly and quickly.
Generally, yes. BFS is the foundation.
But we hinted earlier that standard BFS, just a simple FIFO queue, introduces two absolutely catastrophic problems for large-scale crawling.
Exactly right. Standard, naive BFS has zero inherent understanding of the real-world operational environment it's running in. Problem number one is impoliteness.
Which we touched on with the politeness characteristic.
Yes. When we download a page, think about all the links on it. Navigation bars, footers, sidebars. Most of those links are internal links, pointing right back to pages on the same host.
Okay.
If a standard FIFO queue immediately releases all those dozens, maybe hundreds, of newly found URLs from the same host, and we have thousands of parallel downloaders just grabbing the next available URL,
Yeah.
what happens?
Yeah, if they all hammer that one poor server simultaneously.
Bingo.
Well,
Instantaneously. Hundreds of requests hitting a single host at the exact same moment. That is the perfect recipe for an unintentional DOS attack.
and you get blocked. Okay, so standard BFS is inherently impolite at scale. What's the second major problem?
The second problem is lack of priority.
Meaning?
Standard BFS treats every single URL it finds as equally important. A link discovered buried deep within some obscure spammy forum discussion is given the exact same priority in the queue as a link to, say, the New York Times homepage, or the Apple Investor Relations page, or a critical government health update.
Oh.
The web is just too vast and too varied in quality to afford this lack of discrimination. We must find ways to crawl the most useful, most important, most timely content first to maximize the effectiveness of our limited resources, that 400 QPS budget. We can't waste it on junk if high-value pages are waiting.
Okay, so impoliteness and lack of priority. This means the real engineering magic, the innovation, rests almost entirely within the design of that URL frontier. Turning that simple queue concept into a sophisticated traffic controller, purpose-built to solve both impoliteness and priority management at the same time.
That's exactly where the complexity lies.
Let's start with politeness enforcement. How does the frontier stop us from DDoSing sites? You mentioned back queues.
Right. The core constraint is non-negotiable. We must ensure that only one download thread is fetching a page from a specific host, like Amazon.com, at any given moment. And after that download finishes, there must be an enforced delay in several seconds before we allow any thread to request the next page from that same host.
One at a time per host with a waiting period. How do you enforce that across potentially thousands of parallel downloader threads all wanting work?
We implement a clever two-tier queue system within the frontier. The key is a mapping table. This table maintains a connection, mapping every unique host name, like Amazon.com, Wikipedia.org, BBC.gov.uk, to its own specific separate FIFO queue. We call these the back queues, maybe labeled B1, B2, B3, and so on. Each host gets its own dedicated queue.
Okay, so if my extractor finds 10 new URLs from Amazon.com and 10 from Wikipedia.org, they don't just get dumped into one big general pool.
Correct. There's a component, let's call it a queue router, that sits before the back queues. It intercepts all the newly validated filtered URLs. It looks at the host name of each URL and uses the mapping table to ensure that all 10 Amazon URLs land in Amazon's dedicated back queue, say B1, and all 10 Wikipedia URLs land in Wikipedia's back queue, B2.
Ah, I see. Segregation by host.
Exactly. Then, the actual worker threads the downloaders aren't just grabbing randomly. Each worker thread is assigned to draw tasks exclusively from one specific back queue at a time. When it finishes a download from queue B1, Amazon, it waits the required delay period, and then it can request the next item from B1 if one exists. This structure guarantees sequential download from any single host and enforces the delay, completely isolating the traffic per host and preventing that parallel flooding.
That seems incredibly effective for politeness, but I have to ask, what happens with a truly massive site, like a major news aggregator or a huge social media platform that might generate millions of near valid links in a single day? Doesn't that specific back queue dedicated to that one super popular host just become enormously long, a massive bottleneck where links wait for ages?
That is the absolute core trade-off engineers wrestle with here. Politeness does inherently sacrifice some maximum potential speed for the sake of network etiquette and long-term operational robustness.
Yeah.
You absolutely will see certain back queues, the ones dedicated to very popular or frequently updated hosts, grow enormously large.
So how do you manage that?
The solution is usually about resource allocation. You might dedicate more individual worker threads specifically to service those high-volume back queues. You might ensure those queues have access to higher bandwidth capability. But the fundamental rule, strict sequential ordering, one request at a time per host, with the delay, is always maintained. It becomes a necessary, managed bottleneck because the alternative is getting blocked entirely, which is far worse.
Okay, that clarifies the politeness mechanism through back queues and routers. Now let's switch gears to the other side of the frontier, priority management. How do we make sure we crawl the most useful stuff first? You mentioned front queues for this.
Right. So first, we need a way to quantify usefulness or importance for any given URL.
How do you measure that?
It's usually based on several calculated metrics. The most famous one is PageRank, which Google developed. It essentially assesses the importance of a page based on the number and Crucially, the quality, the PageRank, of other pages that link to it. A page linked to by many important pages is likely important itself.
Okay, PageRank is one. What else?
We also look at things like estimated website traffic. Popular sites are generally more important to keep fresh. And another critical one is the page's historical update frequency. A major news homepage that updates every hour is far more valuable to recrawl frequently than, say, a static personal blog page that hasn't changed in 5 years.
Right. Timeliness matters. So there's a component, maybe called the prioritizer, that takes all these metrics, PageRank, traffic, update history, and calculates a priority score for every single URL that enters the frontier.
Exactly. It assigns a numerical score reflecting its estimated importance. Based on that score, the URLs are then sorted and distributed into a different set of queues. These ones called front queues, maybe F1, F2, F3, and so on, where F1 contains the highest priority URLs, F2 the next highest, etc. This creates a clear hierarchy of importance within the frontier, separate from the politeness queues.
Okay, so we have high priority URLs sitting in queue F1, medium in F2, low in FN. How do we make sure the system actually works on the high priority queues first without completely starving the lower priority ones? We still need to eventually crawl everything, right?
Good point. We can't just only pull from F1 or new sites would never get indexed. The solution is a biased selection mechanism. There's a component, let's call it the queue selector, that chooses which front queue to pull the next batch of URLs from. These URLs then get routed to their respective back queues for politeness.
And it's biased.
It's biased. It doesn't simply pick F1 every single time. Instead, it randomly selects a front queue to draw from. But the probability of selecting each queue is heavily weighted towards the higher priority ones.
Can you give an example?
Sure. The system might be programmed so that, say, 60% of the time it chooses to select URLs from F1, highest priority. Maybe 25% of the time it selects from F2. And the remaining 15% of the time is divided amongst all the lower priority queues, F3, F4, etc.
Ah, okay, so high-value stuff gets processed much more often, much faster.
Exactly. This ensures that the most important, highest value content is consistently crawled first and kept fresh, maximizing the use of our resources. But critically, it still provides some chance, even if small, for brand new websites or lower ranked pages in the FNQs to eventually get selected and enter the index. It optimizes resource use while still maintaining broad coverage over time.
That's a really crucial distinction, bias selection, not exclusive selection. Okay, one more piece related to the Frontier's job. Freshness. The web isn't static. Pages change. We know we have 1 billion pages a month capacity, but the web is much bigger. We can't possibly recrawl everything every 30 days, so how does the system efficiently manage the recrawl schedule?
Right, recrawling the entire known web frequently is completely infeasible from a resource perspective. So recrawling becomes fundamentally an optimization strategy driven by historical data and priority.
How does that work?
We use the update frequency data we've collected. If our system has observed that a particular page historically updates roughly every 3 days, we schedule it to be recrawled on approximately a 3-day cycle. If another page hasn't shown any change in 5 years of checks,
It gets pushed way down the list.
way down, it gets a much lower recrawl priority and might only be checked every 6 months, or even less frequently. We also layer the priority score on top of this. High PageRank pages, pages deemed inherently important, are often automatically scheduled for much more frequent recrawling, even if their actual content update history is slightly slower or less predictable. It becomes this complex, resource-intensive scheduling problem, often managed by predictive analytics models trying to guess when a page is likely to change next.
We've really unpacked the elegance and complexity of that URL frontier. It's doing so much work managing flow. Now let's turn to the more operational side of things. Starting with the HTML downloader, the component that actually goes out and makes the network request. Before it can fetch a single byte of content, it has a really important mandatory obligation it has to fulfill first. It has to respect the robots exclusion protocol, the robots.txt file.
Absolutely non-negotiable. Before attempting to download any URL from a host, say www.example.com page1.html, the crawler must first check for and retrieve the robots.txt file located at the root of that host, www.example.com/robots.txt.
And what's in that file?
It's basically the webmaster's explicit set of instructions telling crawlers which parts of their site they are allowed, or more often, disallowed from accessing. For example, a major retailer like Amazon might use their robots.txt to explicitly forbid Googlebot or other specific crawlers from accessing things like internal search result pages, user account areas, or shopping cart portals.
And the crawler has to obey those rules completely.
Absolutely. It's a matter of both established web etiquette and, in some jurisdictions, potentially legal requirements. If our downloader just ignored robots.txt and crawled forbidden areas,
We'd get blocked fast.
instantly blacklisted by legitimate sites. Furthermore, think about efficiency. If we have 10,000 URLs to fetch from example.com, we absolutely cannot afford to download and parse example.com robots.txt 10,000 times. It's a huge waste of bandwidth and time.
So you cache the rules.
Aggressively.
Yeah.
The results of the robots.txt check for a given hostname must be aggressively cached. We download and parse example.com robots.txt only once per cache expiration period, store those rules locally, and then apply them to every subsequent URL request for that same host from the cache. Critical optimization.
Okay, speaking of speed and optimization, let's quickly detail the 4 key strategies the system relies on to actually sustain that target of 400 QPS, or even peak at 800. Number 1 seems fundamental to any large system: distributed crawl.
Yeah, you just can't do this on one machine. To handle the sheer load, the entire known URL space is partitioned. It's split up into manageable subsets. These subsets are then distributed across potentially hundreds or even thousands of individual servers.
And each server does its part.
Each server runs multiple downloader threads, and each thread is dedicated to processing URLs from just a small segment of the overall internet partition it's assigned. This horizontal scaling, spreading the work out wide, is the only conceivable way to meet that kind of volume requirement.
Okay, distributed load. Strategy 2 tackles a classic performance bottleneck in networking: DNS resolution.
Ah, yes, DNS. Turning the name www.example.com into the IP address. In many basic systems, this DNS lookup is a synchronous operation.
Meaning the thread just waits.
Exactly. The thread making the request is completely blocked, doing nothing, just waiting often for 10 to maybe 200 milliseconds, sometimes longer, for that domain name to translate to an IP address. Now, if we need to make 400 requests every second, we absolutely cannot afford to have hundreds of threads sitting idle waiting for DNS responses. The cumulative delay would cripple our throughput.
So the solution:
Maintain a highly optimized local DNS cache right on the crawl servers, or very nearby. By storing the results of recent or frequently used domain-to-IP mappings locally, we drastically reduce the number of times we need to make those external, slow, synchronous DNS calls. We bypass a major speed impediment most of the time.
Makes sense. Cache everything. Number 3 relies on physics and geography. Locality.
Right. The speed of light is unfortunately a hard physical limit we can't engineer around. Network latency matters. If our main crawl servers are all located in, say, London, and they're trying to fetch a page hosted on a server in Singapore,
Takes time for the request and response to travel.
adds up quickly, especially 400 QPS. To minimize these download times, the crawl servers themselves need to be distributed geographically. We try to place clusters of crawl servers physically closer to the regional concentrations of the website hosts they are primarily intended to crawl. European servers crawl mostly European sites, Asian servers crawl Asian sites, and so on. And this idea of locality also applies to things like caching and maybe even parts of the storage, keeping frequently needed data close to the computation.
Smart distribution. And the final optimization you mentioned deals with the fact that not all servers out there are reliable. Short timeout.
Yeah, the web is full of servers that aren't perfectly maintained. Some are just incredibly slow, maybe they're overloaded, maybe they're configured badly, or maybe they're just temporarily down. If our downloader thread tries to connect and just waits indefinitely for a response that never comes.
That thread is stuck, wasting resources.
Exactly. That precious worker thread is tied up, unable to do useful work, slowing down the entire pipeline for everyone else relying on that pool of threads. So we must implement a strict, predefined maximal wait time, a short timeout. If the target host doesn't respond within, say, 10 or 15 seconds, the exact time is tunable, the download job is abandoned. The URL might be marked for a potential retry much later, but crucially, the worker thread is immediately released to move on to a productive task on a different host. Don't wait for stragglers.
Okay, cut your losses quickly. Moving beyond just speed to overall system resilience, when you have thousands of servers involved, how do you ensure the workload stays balanced? And maybe more importantly, how do you handle servers being added or removed for maintenance or scaling up without causing chaos?
This is where a technique called consistent hashing becomes pretty much mandatory for load distribution, especially for assigning URLs to specific downloader servers or perhaps managing distributed caches.
Consistent hashing, how does that help?
When you have thousands of downloaders, you need a robust but also decentralized way to decide which specific URL should be processed by which specific downloader server. Consistent hashing provides a clever mathematical method to distribute this load fairly evenly across all the available servers. But the crucial benefit comes when the set of servers changes.
When you add or remove one.
Exactly. If you need to take one server offline for maintenance, or maybe you add a whole new block of 50 servers to handle increasing volume, consistent hashing ensures that only a very small fraction of the existing URL assignments need to be moved or reshuffled to the new server set. It minimizes disruption and maintains stability during these common scaling events, which is really hard to do with simpler hashing methods.
That's clever. And what about guarding against the truly unexpected, the power outage, the major software bug? You can't afford to lose the progress of a 5-year, 30 PB crawl if something crashes.
Absolutely not. We must implement robust mechanisms for saving crawl states and data frequently and reliably. All the critical data, the current contents of the URL frontier, including all those back queues and front queues, the massive URL scene records, the status of jobs that were currently in progress, all of this must be consistently snapshotted and written to persistent storage, like a distributed database or file system.
So you can pick up where you left off?
Precisely. If a sudden crash occurs, hardware failure, network partition, whatever the system can be restarted, load the last successfully saved state from persistent storage and resume the crawl almost exactly where it left off. This minimizes data loss and, just as importantly, maximizes the system's overall uptime, essential for long-running massive tasks.
Okay, let's circle back quickly to extensibility. You emphasized that modular design earlier. How does that practically help future-proof the system?
It really is the difference between being able to iterate and improve the system over time versus facing a catastrophic multi-year redesign every time a new requirement comes along.
Right.
Every component we've discussed, the downloader, the parser, the URL filter, the frontier itself, must be designed with very clear, well-defined interfaces or APIs. So if next year the business decides we need to plug in a specialized web monitor module that only looks for specific financial data patterns,
You just build that module.
you build that module to conform to the existing interfaces. Maybe it plugs into the output of the content parser, or maybe it adds rules to the URL filter. The core architecture, the main data flow, remains largely untouched. We just connect the new module to the appropriate flow points. Same if we wanted to add a PNG downloader module, it would likely interface with the URL filter to select PNG URLs and the content storage to save the images. It allows for plug-and-play evolution.
Makes perfect sense. Okay, finally, let's talk about the really dark side of the web, the kinds of problematic content that our robust system has to actively detect and avoid just to survive and not waste all its resources. You mentioned 3 main types.
Yeah, 3 big categories of trouble. First is redundancy, which we already covered with a content scene check. But it's such a massive resource drain that nearly 30% of the web that it bears repeating. We absolutely rely on those efficient hash value comparisons to discard the vast majority of duplicate content before it ever consumes valuable storage or downstream processing cycles. Huge efficiency win.
Okay, dealing with duplicates is paramount. Second, you mentioned the truly malicious stuff, spider traps.
Right. A spider trap, sometimes called a crawler trap, is basically any web page or structure of web pages intentionally or unintentionally designed to cause a web crawler to get stuck, consuming excessive resources, often by leading it into an infinite loop.
What does that look like in practice?
It could be something like an infinitely deep directory structure, maybe generated by bad server-side logic, like absiety going on forever. Or maybe dynamic calendar pages that can generate unique URLs for every possible second of every future century if you keep clicking next month. The crawler just keeps finding new URLs indefinitely within the same useless structure. Automated detection of these is notoriously difficult because they often look like legitimate pages at first glance.
So how do you fight something that's designed to look legitimate but be infinite?
You generally have to impose some external artificial limitations. A common technique is to set a maximal acceptable length for a URL string. If the URL extractor generates a URL that exceeds, say, 2,000 characters,
You just discard it.
you discard it immediately, under the assumption that it's highly likely to be part of a trap or just badly formed data. Sometimes, however, really complex or cleverly disguised traps require manual intervention. Human engineers might need to identify the problematic host or URL pattern and write a very specific custom rule for the URL filter to explicitly exclude that site or pattern. Sometimes specialized blacklisting algorithms are needed to learn and block trap domains automatically over time. It's an ongoing battle.
Okay, avoiding infinite loops. And the final type of problematic content you mentioned was just general data noise.
Right. Data noise refers to content that successfully gets downloaded and parsed, but provides essentially zero value for the intended purpose, like search indexing. This could include massive blocks of automatically generated JavaScript code snippets embedded in pages, large chunks of boilerplate text, navigation elements repeated on every page, maybe embedded advertisements or URLs known to point to high-volume comment spam sections. The goal of both the URL filter before downloading and the content parser after downloading is to become sophisticated enough, perhaps using heuristics or machine learning, to identify and strip out as much of this noise as possible. We want to ensure that we only commit relatively high-quality, relevant data to fill up our precious 30 PB index. Keep the signal, discard the noise. Hashtag tag outro.
Wow. This deep dive has really laid bare the incredible complexity involved in scaling what seems like such a simple algorithm. We define those mission parameters, 400 QPS baseline, 30 petabytes of storage that set the stage,
The numbers really drive the design.
and we established those four cornerstones: scalability, politeness, robustness, and extensibility. They guide every decision. And we saw how that highly customized URL frontier, the brain, manages the critical tasks of prioritization and courtesy using its dedicated front and back queue structure.
Yeah, the frontier is really the heart of making it work at scale. And then we outlined those essential optimizations that make the high performance even possible, from distributing the crawl geographically and using local DNS caching to employing consistent hashing to manage the dynamic load across thousands of downloaders. Designing and running a web crawler at this scale is arguably one of the most sophisticated and challenging undertakings in distributed systems engineering today.
It really sounds like it. Which brings us naturally to the ultimate next frontier. We focused heavily today on crawling static HTML pages. But what would you say is the single biggest technical challenge currently facing the evolution of crawlers, especially when dealing with the modern, much more dynamic web?
Oh, the biggest challenge right now is almost certainly handling server-side rendering, SSR, or more accurately, client-side JavaScript execution for dynamic rendering. Our entire discussion sort of assumed that the links we need to extract are right there, visible in the raw HTML source code that the downloader fetches.
But that's often not true anymore, right?
Increasingly not true.
Mm-hmm.
Modern websites rely very heavily on client-side scripts, mainly JavaScript, using frameworks like React, Angular, Vue, or AJAX calls to generate significant parts of the page content, including the navigation links, after the initial, often quite minimal, HTML page loads in your browser.
So if our crawler just downloads that initial static HTML source code, what does it see?
It might see an almost empty page, maybe just a basic HTML shell and a big script tag pointing to a JavaScript bundle.
Mm-hmm.
It completely misses all the important content and, crucially, all the navigational links that are only generated and inserted into the page by that JavaScript code executing later.
So the crawler hits a dead end. It can't find any new URLs to follow.
It's exactly. To solve this fundamental problem, a truly modern web crawler cannot just be a simple HTTP client anymore. It must effectively act more like a headless browser.
Meaning
It has to download the initial HTML page, then it needs to actually execute the associated JavaScript code within a secure, sandboxed environment, like a headless Chrome or Firefox instance. Wait for the page to fully render dynamically, and then extract the links from the final rendered state of the page document object model.
Wow. That sounds computationally expensive.
It adds an entirely new, significant layer of computational complexity and resource demand. Executing JavaScript is much, much heavier than just downloading HTML. This drastically increases the cost, both in terms of CPU time and memory required per crawled page. It changes the economics of crawling significantly.
That really does change the whole equation. Suddenly you need massive CPU power for every single URL fetch, not just bandwidth and storage.
It absolutely does. And that's just one major challenge. Other huge areas involve building even more advanced reliability mechanisms, like sophisticated database replication and sharding strategies to guarantee data durability across those 30 petabytes. There's also the constant need for better horizontal scaling techniques for all the stateless processing components, and the increasingly vital role of advanced analytics and machine learning for fine-tuning everything, predicting update frequencies, identifying spam and traps more effectively, prioritizing content with even greater precision. It's a field that never stops evolving.
Which leads us perfectly into our final thought for you, the listener, to ponder. We established that the crawler, due to very real resource limitations, must prioritize which pages it crawls and recrawls. It uses metrics like PageRank and observed update frequency to try and keep the index fresh and useful. Now, if the very act of building this map of the web involves inherently prioritizing the historically important sites via PageRank and the sites that change most often, what potential informational bias might this unavoidable prioritization introduce into the index itself? Is the view of the web that the crawler constructs and therefore the information you receive through a search engine always reflective of objective reality? Or is it subtly shaped, inevitably, by the algorithm's constrained, resource-driven definition of what constitutes importance or usefulness? Something to consider the next time you rely on this truly incredible, complex system to find your answer online.